Yeah, warm welcome from me to the participants. Thanks for joining this lecture today. And yeah, in today's lecture, I like to take you on a geological trip back in time. And yeah, we are going to travel to explore the Neoproterozoic and Cambrian strata at the edge of Baltica. And the field photo already nicely shows the exposure, superb exposure along the coastline of the Dicamolin Peninsula. And if you do field work in such a remote place, of course, you need a tent. But if, let's say, time travel would be possible, what else would we need? So if you would, let's say, make a time travel to the Neoproterozoic Cambrian, what would be essential to take with us? Certainly for the Neoproterozoic, we would need warm clothes to stand the icy conditions during the Neoproterozoic. As we know, there have been some snowball earth conditions, and after the snowball earth events, also minor glaciations occurred. And then when we moved to the Cambrian, the climate was quite different. So we would also need some summer clothes for the hot climate during the Cambrian, maybe having an ice tea as well. But the most critical part would be we would need actually an oxygen mask and a storage tank due to the low atmospheric oxygen levels. And this is the most critical, I think, also for the evolution of life. And I will come back to this in the next slide. Here we see time range from 1.5 billion to modern times. And in the lower image, we see the deep ocean oxygenation. And in the upper image A, we see the evolution of the atmospheric oxygen content. Those are models, of course, difficult to get precise values, but what we see in general in the Mesoproterozoic and Neoproterozoic with very low oxygen contents. The deep oceans were anoxic most of the time. A change happened in the mid-Neoproterozoic and onward, and also the atmospheric oxygen levels were quite low with some fluctuations. And the critical time interval of interest is for us the late Neoproterozoic and Paleozoic, where we had some severe glaciations. We have the Sturzian glaciation, we had the Marinoan and the Geschgiers, and there are also a few younger ones, but the main ones known in literature are given here, and they are indicated with this vertical yellowish lines happening in the late Neoproterozoic. And this is also the time where the oxygen content has changed in the deep ocean and in the atmosphere. As we see, we have a change from anoxic, mainly anoxic in the deep ocean, and then it becomes more and more oxic, changes anoxic again, and then mainly in the Paleozoic, we have our oxic ocean. And the oxygen content in the atmosphere changed as well. And especially from the late Neoproterozoic, we see we have a large increase in oxygen content. And during the late Neoproterozoic, we had an oscillation of the oxygen content between 1 and 50% of nowadays level of the present atmospheric level, PAL. And very critical looks like for the evolution of life is the threshold of oxygen, set here in this publication by Krause et al. From Science Advances at about 10% of present day's level. And this is a time interval, as we see, if we come really to the latest Neoproterozoic, younger than 600 million years before present, we see we have the wide oxygen content, and other conditions have changed, so it looks like it was possible that life, macroscopic life, could flourish. And this macroscopic life, which was flourishing at this time, among others, is the famous Ediacara fauna. And this Ediacara biota, there are several assemblages, and the three assemblages which are distinguished is the Avalon assemblage, it's the oldest, and we have the White Sea assemblage, and the Nama assemblage. The names are according to the type localities where these organisms were first described. And in the figure, we see a chart through time and what type of organisms we had. And during the time of about 560 to 550. We have the White Sea assemblage, where the Ediacara biota has the highest diversity. And the study area Northern Norway also belongs to the White Sea assemblage, as I will show later on. But then, during the latest Neoproterozoic, something happened, given here, where we have with question marks, 2 extinctions, and this bluish field, a warm world was appearing. And these worms which appeared have significantly modified the water sediment interface, because before the worms appeared, the boring was mainly, this time also late Neoproterozoic, more horizontal. We had lots of algae maps. And then later on, during the latest Neoproterozoic, and especially in the Cambrian, the organisms went down into the sediment. We had more biodispersion, mixing of sediment, and this has changed also preservation of our organisms, most likely, or our fossils. The fossil record might be biased. Here again, I just took a figure from the famous book, Fedonkin et al., 2007, The Rise of Animals, with nice, colorful illustrations about the Ediacara biota. During the Neoproterozoic, shown on the left side, and we had at the sea floor extensive marine microbial mat grounds, and then our Ediacara biota most likely was some were fixed, local, others were moving around and maybe using this as food. And then during the latest Neoproterozoic, this warm world appeared, and especially in the Cambrian, we had boring. Vertical biotopation was prominent and has changed our sediment water interface significantly. And this change we can observe in the field, several study areas in the world where we can study this Ediacara type fauna, and also then the transition into the Cambrian. And here on this map are some of the famous localities. It's not showing all the places where we can have, or where Ediacara metazoans were found, but the most famous are shown on all the continents, more or less, almost. And our area of interest is here in northern Norway. It's in Tanafjorden, or along the Tanafjorden. Here we see some simplified columns for different areas where this Ediacara biota was found, where we have these macro fossils. In many of those localities, we have sedimentary rocks, which were formed during the so-called snowball Earth event during the Cryogenian. This is the oldest strata shown here. And then some of the successions also preserve some younger glacial succession, Geschkir's type locality in Newfoundland, but similar rocks are also found in Norway. And after this glacial event, which happened about 508 million years ago, worldwide, in different places, these macroscopic organisms appear. And one locality is in northern Norway. It's in Finnmark. And the first publication where these fossils were described from Finnmark was 1992, paper in Geological Magazine. And then after this, it was very quiet. Nothing has happened. And only in very recent time, during our project work, new discoveries were made. And we even found Ediacara type fossils in much older strata, let's say in older units previously known, and also new Ediacara type fauna, which was not known so far from northern Norway. So it's a quite exciting place to work. The project was founded by the Research Council of Norway. The project PI is Annette Högström. Project is still going on, and the funding is finished. Uppsala University, Magne Højberget from southern Norway, Søren Jensen, he's in Spain, expert on trace fossils, especially late Neoproterozoic Cambrian trace fossils. And myself, currently in Freiberg, Theo Balachos, expert for aquitars, and Wendy Taylor, currently in Cape Town. And also we had master students and PhD students involved in this project. And lots of discoveries have been made. The study area, as I said, northern Norway, located between two origins. We have the Timanids, shown here in this map on the edge of Baltica. It's the old origin, which formed during the late Neoproterozoic, and then during younger times, mainly Silurian-Devonian, we have the Caledonites, and at the intersection of both origins, the study area is located, which complicates also the geology slightly. And if you go back in time to the late Ediacaran, here's a paleo map reconstruction redrawn from Mert, publication 2014, Gondwana Research. And at this time, the late Neoproterozoic, late Ediacaran, the study area was located at the edge of Baltica, here with pale blue colors outlined the shelf of Baltica, and in yellow the exposure, the mainland continent. Let's have a look at some Google Map images. The area of interest is located to the west of the famous Varanger Peninsula. Here outlined the Varanger Peninsula. I see my laser pointer, looks like disappeared. Let's see if I can bring it back. Now it's back. The famous Varanger Peninsula, after which the Varanger Ice Age was named, the late Neoproterozoic glaciations. And just adjacent to the west, we have this tiny peninsula here. This is the Diggermolen Peninsula. If we have a closer look, the lower image shown here, the succession of interest, the Ediacaran and the Cambrian, is exposed at the eastern side of the peninsula. The older rocks are on the eastern side, and towards the west, the rocks become younger. And with the dotted line is indicated the boundary, the famous pre-Cambrian, Cambrian, in this case Ediacaran Cambrian boundary. And it's such a nice locality, you can really almost put your hand on the boundary. When you walk along the exposure, I will show some image later on, you can really narrow down within half a meter or so where this famous boundary is located. And as the image already illustrates, it's quite a remote place, so it's difficult to go there. I will talk about it later, but first have a look at the geology. The study area, Diggermolen Peninsula, belongs to the Geyser Nepp complex. So we have several neps in Norway, and here the area belongs to the Geyser Nepp complex. Luckily, the rocks are only experienced a low-grade metamorphic overprint during the Caledonian orogeny. If we go more towards the west, we see this yellowish color, this orange or greenish colors. The rocks experienced higher temperatures and pressures during the Caledonian orogeny. So we are closer to the, how to express to the main part of the Caledonian orogeny. Here we are more on the distal part. The rocks are less influenced. And this is good for the fossil preservation, otherwise not much would be visible. Let's have a look at the geological map. As already said, The rocks of interest crop out along the eastern side of the Dickermühlen Peninsula. We see our Ediacaran succession with number 1, the Nyborg Formation. It's an interglacial succession after the snowball Earth event. Then this number 2 indicated the Mortinus Formation, which is a glacial succession which corresponds to the Gasquez glaciation in Newfoundland with an age of about 580 million years. And then in 3 Lillevanne member, in Relva, in this greenish color with 5 outland Mantrap-Selva. And within the Mantrap-Selva member, in the upper part, there's the boundary. There's the pre-Cambrian boundary located. And then we come into the Cambrian, and all the rocks dip with a low angle towards the northwest. And this provides a nice exposure along the eastern part of the peninsula. So you can really, if you walk along the rivers, which some cut more or less perpendicular, or they are flowing perpendicular, or with a low angle, with strike. So you just walk along these river sections, and you walk from old to young throughout Earth history. And then you can also walk along the coastline. Then it takes longer to reach a younger strata, but of course, it's also possible with nice exposure. In general, the Dickermühlen Peninsula has a size of about 30 kilometers in northeast-southwest direction, 10 kilometers in northwest-southeast direction. And the main focus of the project was on the southeastern side of the peninsula, studying the Ediacaran and Cambrian strata. It's a remote place, how to go there. You can take a small plane flying from Copenhagen or Oslo to reach some place more to the north, Tromsø or Lakselv. This is possible. And then you need some cars. Of course, 100 years ago or so, you could go by reindeer. Nowadays, it would take too much time, so we prefer to rent some cars. You have to take all the stuff with you, what you need, your tents, your food, your equipment, boxes for samples, and so on. Quite a long drive from Germany. You have to calculate in total 3 days from leaving Germany until you're on the field. So even though we live in Europe, but it's a very remote place, and you have to calculate enough time for your field work. And if you forget anything, it's not good, because you cannot go back to a supermarket and buy what you forgot. You have to take everything with you. You have to make a good planning before you leave, go to the field. Then you have to move everything to a boat. As I said, it's a peninsula. There are no roads. You can only go by boat or helicopter, but helicopter costs several thousand euros per day. So the cheapest version is a boat, and it's also more efficient. Moving all to a bigger boat, and then about 3 hours, you go out the fjord, Tanna Fjord, and then with a smaller boat, you have to transfer several times everything from the larger boat into the smaller boat. Then you go to shore, unpack again, back to the larger boat. Takes some time until all the scientists, the luggage, and so on is at the coastline. And then you say goodbye to the shipman, and hope he comes back after 2 weeks, picks him up. Otherwise, can be unpleasant maybe if you run out of food. Then you set up camp, and then you can already start fieldwork, because wherever you set up camp, you're already surrounded by the rocks of interest. If you set up the camp more in the southeasternmost part, you have the campsite maybe in the Ediacaran. If you set up camp more along the coastline, more to the northeast, then you set up camp in the Cambrian, and you can start studying the outcrops. Fieldwork in such a remote place involves lots of walking. You start in the morning, and then till the evening you walk around, you study sections, you try to find new sections. And then again, lots of walking all the day. Sometimes you spend maybe half a day at the same locality because you found interesting fossils, and then you try to collect more and more fossils. But in general, lots of walking, packing your rucksack full with specimens, carrying it down from the hill down to your campsite. Even though it's exhausting, but it's great fun. Be prepared for all weather conditions. Fieldwork is only possible in summertime, because otherwise everything is covered in snow. And even in summer, if you go in July or August, there are still snowfields in the highest parts of the peninsula. So you need also warm clothes, and there can be also thunderstorm coming. So yeah, be prepared for all weather conditions. And there's also some wildlife, and often you also see some reindeers passing, and especially when you set up campsite during the night, because the campsite you always set up where a river is, because you need fresh water for cooking and drinking. And then the animals are thirsty, and during the night, late evening, they come down to the fjord, to the riverside, and they will cross over your campsite. But they are peaceful. They don't destroy your tents. They are very peaceful animals, but you only hear them when their voiceovers they make. Let's come to the geology. Why is Diggermole Peninsula of great interest for geologists and paleontologists? Some key facts about the peninsula. It comprises about 2.5 kilometers, mainly of silicic rocks. The rocks experienced only low-grade metamorphic overprint of about 200 to 250 degrees Celsius, according to the color of organic gold microfossils. And it contains the most complete Ediacaran-Cambrian transition in Scandinavia. And, most important, of course, it contains the only Ediacar-type fossils in Scandinavia. And in the next couple of slides, I will guide you through the geology from old to young, show you some field exposures, some fossils, so that you get a feeling why it's so exciting to do field work in Arctic Norway. Let's start with the Morteness glacial succession. Here are some field photos showing some diamictites with extra basinal clasts metaquartzites, igneous rocks, and we are swimming in a silty, fine sandy matrix, poorly sorted, typical what you would expect from a diamictite. And this strata is correlated with glacial successions on Newfoundland. In Newfoundland, the succession has been dated and has an age of 580 million years. So if we assume the correlation, the lithostratigraphic correlation is correct, we have an age marker, we can say our Morteness formation has an age of about 580 million years. And if so, above this glacial succession, at some point, there should be fossils appearing. And indeed, we found now the oldest non-stromatolite macrofossils in Scandinavia, Paleopachychnus. It was known before, but now we have it from the lowermost level. So we really found the oldest occurrence of this fossil, Paleopachychnus. And the age range in Avalonia and Baltica is from 565 onwards. So that means if we really know, okay, this is now the oldest occurrence we have another age marker, we can say, okay, somewhere in the lowermost part of the interelva member, our succession has an age of 585, based on this non-stromatolite macrofossil, Paleopachychnus. And this fossil, they are very tiny, difficult to find actually. So we studied this outcrop during several field seasons, and only, I think, during the third field season, we found these fossils. Even so, we studied this special exposure several times, but you need certain light conditions, and it depends if it's wet or dry, because they are very tiny, a few millimeters in size, so can be easily overlooked. These are bedding plane parallel modular fossils consisting of simple or more complex series of closely spaced millimetric circular, sausage, or kidney-shaped units. And each unit has walls forming subspherical or cylindrical chambers. And some illustrations are given here on the lower right side, and everything has been published in Jensen et al. 2018 in Bulletin of Geosciences. And then if we walk along the coastline, and already 15 meters, about 50 meters above our Paleopachychnus, the first disc-shaped fossils appear. And this appear in several layers throughout the succession, the interelva member. And these disc-shaped fossils, they are called aspidella. point for scale is given here. So they are a few centimeters in size. They can be very small, maybe just 2 centimeters, up to 15 centimeters in size. They are disc-shaped fossils, and they are interpreted as holdfasts. And the reconstruction is given in the lower image. What is preserved nowadays in our rock record are the disc-shaped parts. So most likely that the organism was attached to the sediment. This is our Aspidella. And then higher up in the succession, we also found other Ediacara-type fossils. Some look similar to Swapuntia, others are similar to Dickinsonia, but not yet published, so I don't show images, but I can mention already. It's also in abstract form, at least mentioned already. And if we take all this information together, most likely at the edge of Baltica during the Ediacaran time, it was looking like shown on this image here. Here, different types of Ediacara biota, Rangiomorpha, Dickinsoniomorpha, and then our Triradialamorpha we also found, and also these Ernitomorpha, where Swapuntia is a part. And this is, yeah, let's say, how it could have looked like at the edge of Baltica during the late Ediacaran. And a problem could be the cleavage. As I said, the rocks were overprinted during the Caledonian orogeny. So you have to find exposure where the cleavage is with a very low angle with the bedding or plus minus parallel. This is an ideal place to look for fossils. Otherwise, your rock falls in pieces and not much is preserved. Then we can study the underbeds of coarser layers. We have some nice soil marks. We can measure the orientation, the long axis. You can rotate your the bedding back to horizontal, and then you get information about the paleo-current direction. If you move higher up and now approach the Precambrian boundary, here is a field image, and just about we have on the image here, there's MA2, this is Mantrap Selva member 2, and just above, maybe half a meter, 1 meter above this more quartzitic unit, most likely at this locality here is our Precambrian boundary based on the fossil record. What we find Gyroliths. These are some spirally coiled trace fossils which go already into the sediment. And then an index fossil, we have Treptichnus pedum, also called in older literature Ficotis pedum. And yeah, it's the earliest widespread complex trace fossil, and the first appearance of this trace fossil defines the base of the Cambrian. So we know here we are already in the Cambrian. And we can put our hand more or less on the boundary. Then we move high up in the Great Vicar. Always when you make such field trip, don't forget to make a lunch break. And while doing a lunch break, you can also observe the rocks left and right. And sometimes you discover some interesting rocks you didn't expect actually, and you can find new fossil exposures, as happened here in this locality, because then you find maybe Sabelliditis. This was also known before, but now we have a more detailed record from the Dicamonian Peninsula. It has been recently published. It's in Eppestad et al. 2022, Geological Magazine, open access available. And the Sabelliditis cambriensis, it belongs to the Annelida. It's a worm-like metazone consisting of long, flexible tubes with coarse to fine traverse ringling, thick walls, and a constant tube diameter up to 3 millimeters in width. And on some rock slabs, you can find several of the specimens. You see these tiny blackish lines. Each of these tiny blackish lines is actually one Sabelliditis, and some are full. Now you just cut the rock, and then if you're lucky, in some layers, it's full with Sabelliditis. So something happened to them, mass extinction, and then they are preserved. Then higher up in succession, the Cambrian becomes more coarse. We have coursing upward sequences, some parasequences, fin-bedded fine sandstones, siltstones, then figure-bedded sandstones. And in the Cambrian in general, a lot of trace fossils in some of the units, especially in the Dulbe Geyser formation. Now, here we're already a bit higher up in the Cambrian Dulbe Geyser. We find lots of trace fossils. Many of them are associated with arthropods, especially trilobites. And the two famous trace fossils, I guess everyone knows, we have Cruciana. This is when the organism moved through the sediment. And we have also Usophycus. This is when the organism was resting on the sediment surface. And you find several of these traces throughout the succession, throughout the Dulbe Geyser formation. So it was really very lively, the seafloor. We have indications for shallow water conditions. We see symmetric wave ripples. We have our Cruciana traces, and then we see also here nicely the field photograph showing the succession we can study. This is all Cambrian. This is a lower to middle Cambrian, a fixed succession. You can walk up here, and it's full with fossils, trilobites, trace fossils. You can take samples for microfossils, aquitars, superb succession. And in some of the slabs, they are full with traces. You can check some are worms. We have the worm world fauna, and then some traces are made by arthropods, many trilobites. You can redraw these traces and can say something about the evolution and how certain organisms were living together, or some were hunting the other organisms. And in the higher part of the Cambrian, we have very organic-rich, fine-grained sediments, similar to our alum shale we have in southern Sweden, in the Baltic area. And besides all this field work in collecting rock samples, I collected a lot of samples from the mudstones, from the sandstones, for petrography, bulk rock geochemistry, isotopic studies, including also analysis of detrital circle grains. And I will just in the last couple of minutes show some recent data we obtained from the samarium neodymium isotope study from the mud rocks. Samples were taken across the interglacial glacial succession, so topmost samples from the Nyborg formation. We have samples from the Mortenes formation, and then also from the lowermost part of the Intrelva member. And then we collected samples across the pre-Cambrian-Cambrian boundary to study if something has happened from the pre-Cambrian to the Cambrian. And the data are shown here, recently published in pre-Cambrian research. And big surprise, we didn't expect to see such changes actually based on the isotopic composition. Mud rocks are ideal because they're very fine-grained, they are ideal for such an isotopic study. And we see the oldest strata here analyzed, Freiberg and Mortenes formation. They show more or less similar isotopic values. Here epsilon neodymium is shown. And then after the Mortenes glacial strata, a shift happened. We have much lower epsilon neodymium values, indicates older source material. If the values become lower, older crustal material. If the values epsilon neodymium goes to higher values, 0 or plus, we have younger, fresh material influx. And this is going on through several meters in the lower part of the Intrelva member. And then at one point we have again a significant switch. And interestingly, this shift from lower to higher values plus minus coincides with the appearance of the Ediaca type fauna in our succession. And if we plot the data in another diagram where the epsilon neodymium values are shown on the y-axis and the xdh, we can say something about the likely source areas where the material was coming from for our fine-grained sediments. So a majority is coming from the Svekofenian province, and interestingly, within the succession of the Dicamonian Peninsula above the Mortenes formation, we have a certain time interval where looks like sediment provenance or the source was more a Karelian province, much older rocks were supplying material. And I just want to illustrate this on a map. showing these different provinces outlined here. So first looks like the Svekofenian province was supplying material, let's say south to north, simplified. And then we have a shift more towards the east to older strata in general. In Baltica, if you go more towards the east, the rocks become older. The oldest rocks are on the Kola Peninsula, so in general trend from younger to older. So we have a shift towards the Karelian province at some point in the lower part of the Ingrelva member after 580 million years. And then more or less with the onset of our Ediaca type biota, we have again a shift back to Svekofenian provenance, plus additionally, most likely, younger volcanic influx, as our isotopic values show lower values compared to Newberg and Morteness formation. And this younger influx is confirmed by detrital circans. Of course, already by a paper, Zhang et al., 2015, they found, among some older grains, they found a lot of younger circan grains with the age of about 50 million years. So in the late Ediacaran, we have also an influx of, and also during the early Cambrian, influx of younger magmatic material. So this fits nicely to our isotopic data. And overall, to stay in time, what have you learned today? So recent fieldwork in Finnmark provided new insights into the rise and early evolution of animals through the Ediacaran Cambrian interval. So based on these new fossil findings, we have now some age constraints because certain fossils, if we assume we have the oldest fossil found orbis in the succession, and if you compare with other areas where the ages are known, so we can say that the Morteness formation, most likely 580, if the correlation with the Geschgiers is correct. Then we have our oldest Paleoplastichnus, and we know the oldest Paleoplastichnus is from 565 million year old sediments. Then higher up, we have a diverse assemblage of Ediacara type fossils, Aspidella, Swapunja type fossils, and Tiginsonia type fossils. And this belongs to the White Sea assemblage. In general, the White Sea assemblage has an age younger than 560 billion years. So we know within the Intrelva member somehow, okay, we have a 568 million year old age marker. And then we have our Precambrian boundary. We have our trace fossil Treptichnus pedum. And according to the new dates from Namibia, the Ediacaran Cambrian boundary is now set at 538.8 million years. So we have another age marker for our succession on the Dickermolen Peninsula. We have provenance data where we can identify some change in provenance through time. These are just preliminary results. As I said, project is still going on. We have to publish many of the remaining data. So I just wanted to give you a first brief overview. But most important is fieldwork is essential. So it's very important also to go back to areas where you may think everything is known. It's not, believe me. Even in Germany, when you go back somewhere, you will discover new things, like these exciting things recently published in Facies, the glandonites from the Jurassic of Germany. So, I mean, lots of discoveries can be made in the field. And with this nice field impression, I would like to finish. And I will just read one sentence from an interesting book. I recommend everyone to read this book. And in this book from John McPhee, it says, rocks are the record of events that took place at the time they have formed. They are books. They have a different vocabulary, a different alphabet, but you learn how to read them. And with this, I thank everyone for listening, and I am happy to answer any questions.